Okay, so the last few videos have all been about the conjugate base side of a Bronsted-Lowry acid-base reaction, right? And the idea that every acid-base reaction is always going to move toward the conjugate, the most stable conjugate base that it can, right? Because the most stable conjugate base is going to be the least reactive, it's going to be the weakest reactant, and so once you get to that conjugate base, that stable conjugate base, your reaction pretty much stops, right? Your equilibrium is going to favor that more stable conjugate base. And so this idea we can then extend and actually use in other reactions. And so in this video, we're just going to really quickly introduce the idea of other reactions that are not Bronsted-Lowry acid-base reaction. We're going to come back to these, so this is not something where you're going to have to understand every instance of it or anything like that. But just to kind of see how this idea of if we can identify what are stable conjugate bases, this actually gives us a lot more information than just is this acid-base reaction favorable. Okay. Okay. So let's look at a reaction, and this is, I don't know where my example went, so we're making one up, right? Let's look at a reaction between 1-bromobutane and let's just we'll use a negatively charged sulfur. Okay. So this reaction, I'm going to tell you right off the bat that this is an acid-base reaction, right? It's we have an acid and we have a base, and so right away identifying which one is which is going to be worthwhile, right? This is our base, and remember that we can also call a base a nucleophile. Because it's negatively charged, that's kind of our clue here. When we see negative charge, we know that that's where our arrows are going to start. That's where our base is. And if that's the base, then 1-bromobutane must be the acid, right? And another word for our acid is electrophile. And so now we would look at this and say, okay, if this is our base and this is our acid, if we're talking about a Bronsted-Lowry acid-base reaction, we would expect the hydrogen from this molecule to be transferred to the base. But of course, in this molecule, all the hydrogens are attached to sp3 carbons. And we know that hydrogens attached to sp3 carbons in general are unreactive, and so instead they are, and they're not very good acids. In fact, they're terrible acids. And so if we just look at this from a Bronsted-Lowry acid-base perspective, these two reactants, will not react with each other. What is the most stable conjugate base that we can make from this process, right? Or put another way, like where is the negative charge the most stable in this molecule? Right? We have a couple of choices. We have carbons, we have sulfur, and we have bromine. And so if we think about this just from a like periodic trends, right? So if we're trying to identify what is the most stable possible conjugate base. Right? Well, sulfur is already our base, so we know this is where we're going to start our arrows and everything, and so we have to react with the acid. So it's a carbon or a bromine. It makes sense that Br minus, right, because of periodic trends, would be kind of the desired outcome of this reaction. That's the most stable possible outcome, would be to generate a negatively charged bromine, because Br minus is the most stable possible conjugate base. So knowing that, now we have two things that we can do. We need to, first of all, bring some electrons to that bromine in order to make it negatively charged, right? So we can have our arrow break that sigma bond and push those electrons onto the bromine to generate Br minus. Right? But of course, if we just do that, that means that this carbon 1 on 1-bromobutane is losing electrons, and so we can also use our base to kind of replace those electrons, right? So that base can bring those electrons to that carbon, and we can make a sigma bond. So we're going to make a sigma bond between sulfur and carbon, and we're going to break a sigma bond between carbon and bromine. And so of course, what this ends up being is just a different flavor of substitution reaction. the sulfur ends up attached here, and the sulfur brings along the 2 carbons that were attached to it before. And now the sulfur is neutral because it was negative and it gave up one of its lone pairs to make this sigma bond. And the bromine ends up negative because it gained a pair of electrons from the sigma bond, is now in a lone pair. And so if we drew all our lone pairs on bromine, which I guess I can do, right? We'd have 1, 2, 3 lone pairs on neutral bromine, and then we've created a 4th lone pair on the negatively charged bromine here. So this is an example of how this is not a Bronsted-Lowry acid-base reaction, right? This is very different. No hydrogens are being transferred or anything, but the concept, the ideas of this reaction are exactly the same. We want to make the most stable conjugate base we can. We identify that that most stable conjugate base is Br minus, and then we figure out mechanistically through a mechanism, how do we make that happen, right? We need to start from our base, right? Our mechanisms always start from the base position. So that negative sulfur is a great place to start. We bring those electrons in to make a bond, we break a bond, and we're there. This is called an SN2 reaction. And the reason it's called SN2, the S stands for substitution, the N stands for nucleophile, because that's what's doing the substitution, and 2 means that you're having 2 molecules reacting together at once, right? So we're having 2 steps occurring at the same time. We're making a bond and we're breaking a bond. So an SN2 reaction is another substitution reaction, just like a Bronsted-Lowry acid-base reaction, except that we're generating our conjugate base, and you can't see me right now, but I'm doing that in quotes, conjugate base, but it is, right? That's pretty much what we're making, is we're making a new stable negative charge there from our acid, from our electrophile. So the concept is the same. So we'll revisit SN2 reactions. There's more to say about SN2 reactions next week, or maybe even the week after that. But I wanted to introduce that here because I think it really kind of nicely illustrates this idea that all this acid-base stuff that we're learning about stable conjugate bases and stuff really easily applies to everything else that we're trying to do. Okay, so next up, we're going to look at addition reactions. So we've been talking about substitutions. Now let's apply this to addition reactions and see how that goes.